So, thanks everybody for coming. It's my absolutely great pleasure to have Miles Simon here. And he will talk about the regularity of Ricci flows coming out of metric spaces. Go ahead.
Miles, you're muted.
I'll try that again. Yeah. Okay, so thanks very much to Armin and Gufong and Philip Reiter for inviting me to this seminar here and giving me the chance to talk. And yeah, it's my great pleasure to be here, digitally be here. And okay, I'll begin. So yeah, I'll be talking about the Ricci flow. And so here's the equation. First, oh, that's not good. It seems to have a few problems there. Okay. First, sort of invented or discovered by Hamilton in 82, and the equation just says, as I'm sure most of you are aware, that you take a family of metrics which are smooth, and they evolve according to this equation here. If they evolve according to this equation here, then you say it's a Ricci flow. Okay, so you can see here, I'm just looking at a short time interval. So time is in 0, 1, or some, maybe it's in, also it could be in 0t, with t less than infinity, maybe. Usually always going to take t less than equal to 1. So I'm interested in short time behavior. Okay, so it's not about what happens when you go to infinity. It's about this short time evolution behavior. And let's see now. If I can get this to work. Right, so that's what I said. I'm interested in this short time behavior. And you'll see that I'm talking about smooth solutions, and you'll see I've actually just put this sort of open on the one side. Okay, so you notice that time 0 is not included. So this is not a typo. It's actually, it's part of the whole story, is that you've got a smooth solution and it's defined up to, but not necessarily including time 0, and goes up to time 1, then you're sort of interested in behavior near time 0. And that's what a lot of this talks about. So by the way, I think you saw on the first page, I hope, that this is joint work with Felix Schulze and Alix Deruelle. So just in case you didn't see that, that is the case. Okay, so let's just go further now. Right. So we're interested in a particular class of solutions which are bounded from below. The Ricci curvature is bounded from below. And the curvature I want to be evolving in such a way that it's less than or equal to c0 squared divided by t for all time in the interval. All time in the interval we're interested in here. And let's see, what else have we got? We want also that once you've got this, so this is just, you know, two conditions here. And once you have these conditions, I'm assuming I'm on a smooth manifold without boundary, then, okay, it seems to have a few problems turning there. Then you see actually that you've got, the metric is controlled. So the metric's going to be controlled in the following sense. It's a typo. So the distance at time t is bounded below from the distance at time s minus c0 times some gamma. Gamma is just a constant depending on n, so it's not a problem. Times by square root of t minus s. This is for t bigger than or equal to s in 0, 1. So you've got some bound from below. You notice, by the way, here I had a c0 squared, and now I've got a c0, so it's sort of the right scaling. And on this side, this is an easy estimate, just follows from this one here. You get that the time is, the distance at time t is less than or equal to the distance at times s times by this exponential function, which is of course bounded and approaches 1 as t and s go to 0. So these estimates, so once you've got these things here, you can just use the Ricci flow equation to get this one pretty easily just by writing down the evolution equation for distance. So this one here is a little trickier. They're both due to Hamilton. You can show them using Perelman's results too, but actually I initially just used some things of Hamilton. And essentially what you do is you have to look geodesics, minimizing geodesics, and you look at you prove some estimates on Jacobi fields along these minimizing geodesics. And actually that's a static result. And once you have that, you just plug that into the evolution equation. You get essentially what this thing here is it's sort of like the integral from, so it's roughly speaking, it's a time integral from s to t of the square root of the curvature. And that's why you get a square root of t minus s essentially, because if the curvature is like c0 squared on t, then you get a c0 divided by, so here I should put a LDL. So that's essentially what you get in order to, so it's saying that the time derivative, sorry, so this is what it says. It says that essentially you can bound the distance by an estimate of this type after integrating in time. So that's where you get this little square root of c0 t minus s. Okay, so these follow from estimates of Hamilton just using the Ricci flow equation. So you've got these nice control on distance. So once you've got this control on the distance, what does that tell you? Well, you can then immediately see that if you go down to 0, things are not defined at time t is equal to 0. But if you go down to 0, so here dt, by the way, I said is the distance with respect to the evolving metric. Okay, so this implies immediately that you get some sort of well-defined limit space or limit metric as time goes back down to 0. And you call this thing d0. Okay, so, and it's a uniform limit, and d0 is really a metric. Okay, so it gives you the same topology that m dt had or mg of t had. So it's not degenerating, and that comes from this side here. You see, if you think about s going down to 0, that should approach d0 a e to the a0t as s goes down to 0. And then you see that d0 a exponential of a0t is bigger than or equal to dt point, right? So that's telling you that d0 is there's something of the metric surviving. The metric survives into the limit. You've really got something which is not degenerating. So you don't have d0 xy is equal to 0 for x not equal to y. Okay, so that's the first thing to notice. So we're just looking at this class of solutions. So it's just these two conditions. Then you get this really useful condition here about the distance, and that's telling you that this d0 exists. That's the first thing you notice. Okay, so nothing else here. I'm not assuming any other information. So you start to think about this, and then you want to ask yourself, well, you want to know more about this limit at time 0. But before we get on to this point, the question is, where does this class of solutions come? So it's actually a very natural class of solution which occurred in various works and in various situations. So here's examples which are in the class. So some time ago, I started looking in the 2-dimensional case and 3 dimensions also. So you start with some sort of metric. So here it is, m, and the initial metric I'm just calling g10. And you assume that it's got scalar curvature being equal to 0. So let's assume it's almost cone-like, but it's flattened out a little bit here. Okay, then if you flow it, then things start, maybe I'll get this picture a bit better here, starts to kind of turn in a little bit and become sort of convex. It starts to smooth out. And here I've got the cone in the next picture even sharper, but it still starts to smooth out. Okay, so it starts to smooth out and the curvature starts to decay, and it's not so high. I mean, here you've got really high curvature at time 0. Okay, but after flowing for a while, the curvature sort of distributes a little bit. It's the usual situation. You've got a battle between the distributive qualities of a Laplacian. So in the evolution equation for the scalar curvature, right? So you've got this, on the one hand, you've got, so this is a g of t here. One hand, the thing wants to smooth out. On the other hand, the curvature is sort of blowing out, and this blowing up. But in this instance, this part wins. So it's an interesting property that somehow the Laplacian here is winning and it smoothed things out. And now what you can do is take a limit of these initial metrics and get more and more like a cone, and then you still get this thing is smoothing out. So you can now take a limit of your Ricci flows above, and that's going to lead you to a solution MGT where t, of course, doesn't go back down to time 0. You've got to stay a little bit away from, sorry, you can't include time 0 now because it's only smooth away from time 0. But in some sense, this thing is coming out of this initial metric here, d0. Yeah, you've got this cone metric, which are called md0, and the estimates CT from before show us, in fact, that mdt is going uniformly as t goes back down to 0 to md0. Okay, so you can describe that using Gromov-Hausdorff convergence if you like, but in fact, it's a uniform C0 convergence. So it's even, it's very simple to describe here. It's just uniform C0 convergence. So I should say locally, yeah, locally in the C0 sense. In the uniform C0 sense, I mean that. Okay, so this is, okay, so I know some people are aware of these examples. I'm just giving you examples that fit in this class, and then I'll come back to the class. So, right, let's have a look at the next one. So that was n is equal to 2, but you can do this for n is equal to 3. But then the curvature condition you want to take is not scalar curvature, but Ricci curvature, for example, or for higher dimensions. So Felix Schulze and I looked at that. You can take the curvature operator, and you can do the same procedure. So I'm taking a limit of things which are approaching a cone, and then the Ricci flow here is smoothing things out, and you get this nice property here that somehow the dispersive qualities of the Laplacian are beating the reaction term, which is like a sort of like a squared term of the curvature. So here what you get is a solution, which is once again only defined up to time 1, but the distance of the involved metrics is going back down to md0 in the same way it did before, uniformly locally. Okay, so the initial metric, there is actually a G0 you can kind of write all around here. So I could write G0, an initial metric away from this tip here. But in the tip, I've got to make some sort of choice, and it's certainly not going to be continuous or smooth there. So G0 is not continuous on the whole manifold on M. But it seems to be that you could expect that it's going to be continuous in regions like here. Okay, if I take this region here where everything's smooth, I'm assuming that I'm approaching, in my initial examples here, I'm approaching something which is smooth away from the tip. So you'd expect that, in fact, that the convergence as time goes back down to 0 is approaching things smoothly away from the tip. And yeah, this is true, but only because of the construction. Okay, so it's a nice, at this point you can see pretty well, it's pretty likely that as you go back down to 0, time goes to 0, that the metric itself, g of t, is going to be smoothly converging to g0 away from this tip, right? And that is the case. You can show that, but that's all to do with the construction. So this is a special example here. I'm actually constructing a solution in this way, okay? So then let's go on. Unless there are any questions. It's a good time to ask questions because it's going to get...
I have a question.
Yes?
So thinking of this from a PDE standpoint, in some sense, you're searching for weak spaces in which to embed your evolution equation.
Yes, yes.
If you're thinking of Sobolev spaces and such things, is that the equivalent? Is that the direction of travel?
So this is a direction of research, but the solutions I'm describing here are actually more geometrically constructed, and they really do have the property that this solution you have, so it's like starting from a weak function and it's becoming smooth as you evolve it by like a heat flow. Yes, there's certainly this property here. It's the smoothing out properties of heat flows. But the way the constructions that allow me to get that are very geometric. So I'm getting, in particular, you remember there was this condition. So all of these things, good, thanks for actually asking. I don't think I even mentioned this. I said they're part of the class. So they must be satisfying this here. And in fact, the Ricci curvature in this instant, the curvature condition is remaining bigger than or equal to 0 for all t. So it's this geometrical condition which allow me then to obtain this limiting solution, which is coming out of something non-smooth. There's of course, people are interested in trying to do Ricci flow for Sobolev spaces or weaker spaces, but that's not how I construct this, or at least that's not what I'm talking about today.
Okay, thank you.
No problem. Yeah, thanks for the question. Okay, yeah, so let's go on. Yeah, it's very geometric, this construction. Yeah, so I think I'll have to do it this way now. Okay, so these are the next examples, and oh yeah, something happened there, sorry. I don't know what happened. To try again. Okay, we're back, yeah. Okay, I think you can see that again now. Yeah, I don't know what happened. Okay, so here are some other examples. So these examples here, you notice in before that all the examples I constructed, what I did was I began with some sort of, some space here, and then I took a limit to get some sort of weak space, and here I took a limit and I'm just getting a weak space in the sense of Gromov-Hausdorff convergence. And then by doing Ricci flow on each of the ones in each of the starting ones, I get something which smooths out, and that leads me then to a solution, which I've called MGT for t and 0t. Now, recently, this whole procedure was really, really brought along here by Richard Bamler, Estecobasis, Rivas, and Burkhard Wilking, in that they didn't just look at curvature operator and Ricci curvature and so on, but they looked in any dimension for a whole bunch of curvature conditions, and they weakened the condition that the curvature operator was, say, bigger than or equal to 0. That was a condition I looked at with Felix Schulze back in 2012. They allowed a little bit of negativity. This is a hard jump, right? So it took a lot of work for them to get this done, but it's a very nice result. As a result, you can actually now take limits of things which have curvature operator or many other curvature conditions which they considered bigger than or equal to some minus constant, now some negative constant. You always need some sort of volume bound from below for all balls of radius 1. You want volumes bigger than or equal to b0. Then you can take this limit and do the same procedure. And you end up in the class, right? So you end up in the class of curvature t less than or equal to c0 squared on t for some c0. And in this class here, you've got c bigger than or equal to some new constant. The way I've done it, you get c bigger than or equal to -1. C is a curvature condition. It's either curvature operator or Ricci curvature or PIC or some other condition that they looked at. And initially I looked at this for Ricci, so I managed to get something done there too, but this has really been advanced now to many other curvature conditions and in all dimensions now. So you can use this procedure and get into the class again. Right, and then you start to think about it and you ask yourself, yeah, well, what about this class? All the solutions that possibly that you get of this type here coming out of something like this. So that's why I call it coming out. Like it's, as you go, time goes back to 0, it approaches it at least in the C0 sense. You ask yourself, you know, what about uniqueness? What about regularity? So there's various other questions if I'm just in the class. So those are the questions that we start to ask. And okay, so here's the class that we're interested in. And right, so you want to know now, so I'm just writing down the class again. Somehow or other see if it's working again. Oh yeah, okay, we're back. We can do this again. Right, so I'm just writing the class down again so you see it again. Right, so that's the class that we're interested in. These are the main two conditions, and that gives you the distance control, and that gives you this D0. But now we're not assuming that you necessarily know what your initial metric is. You just say, let's just assume we're in this class and you want to understand something about the D0. Then you can ask all sorts of questions. Like the ones I just constructed through these examples, are they the only ones that come out of this, these initial non-smooth metrics, uniqueness? You can ask, of course, the question of maybe uniqueness in a certain class, maybe in the class I just mentioned before. That would be very nice, but it's unsolved. These are all unsolved problems. You then start to ask more questions about existence. Imagine you don't construct, you remember these initial D0s I constructed were always sort of like smooth, limits of smooth objects. What if you just begin with something like this? So I just begin with a cone, a metric cone. So I've got some wobbly Sn in here, which has got a smooth metric on it. So it's a cone, a metric cone over this smooth metric. So I'll say it's got an Sn minus 1 there. And you assume that, for example, Deruelle said, let's assume this curvature operator that all the eigenvalues of this metric are bigger than or equal to 1. Then he showed you get a solution coming out which lives in the class. And then, of course, you ask, is this the same solution you get by doing this? Do you always get the same one if I do this smoothing, if I approximate this initial metric by smooth things, right? So he showed you always get something if you start with something like this. You get a solution in the class, but the question is, is this the same one you had before? It's not clear. Anyway, he has some existence results also starting from non-smooth objects. So that's another question. What exactly? So I guess it goes back a bit to the question that was asked before. What conditions do you need on this, some weak conditions on this initial metric space here to guarantee that you get solutions which live in this class, or maybe in some other class? Okay. Right, so here's the question I'm interested in today, is the regularity of solutions coming out of smooth regions. So you remember the picture I showed before, I had this little red region where I said just by construction, the metric g of t goes back to g of 0 in that region. So I'm interested in exactly that question. Is that always the case if I just start with a solution in this class? So now I have to ask Armin a question. How long am I supposed to talk?
45 minutes. That would
okay.
You have 20 plus.
Yeah. Well, my clock's on my computer. I can see it. So I'm, I've got no excuses. I'll get on with it. Yep. Okay. So this is the question we're interested in today. So this is essentially the setup for, of course, there are heaps of other questions, but who knows what they are. Right. So now we need to really get down to the nitty-gritty. And that means we're starting now with just some metric space. Okay. So here it is. MD0 is just some metric space. And you want some way of saying that something's smooth or Riemannian smooth. I'm just going to call it a regular point. So here's the technical details. You call it smooth or regular if you can find a map from the ball BRX0. So BRX0 will just be the ball with respect to this D0. And it goes over to something which lives in Rn. And you want it to be a homomorphism. And you want the metric that you get by pushing forward when it's a homomorphism. I can always define, some sort of metric. You want that this thing that you get, I'll call it D0, is given, it's the distance given by a smooth Riemannian metric G0 tilde. So that's my definition of a smooth region near X0 or a regular point, right? It's a simple definition, but it fits in to it fits into all the situations I'm considering and helps me describe adequately what I mean by smooth region. Because now you're just starting with a metric space and you really want to say this region is somehow smoothly Riemannian near X0. That just means you push the metric over using some homeomorphism and you get something which is coming from or defined, the distance is defined by a smooth Riemannian metric. Okay, so that's quite a straightforward definition. So the notation here is, what is this push forward? Well, it's the only thing it can be. I take 2 points x tilde, y tilde in the image, and I just pull them back using f0 minus 1, and now I use d on it. So that's my definition of this push forward of a metric. It's standard definition. Any other notation? I think so. Yeah, so like I said, what is BR up here? I said BRX0 or BRZ. That's the ball. I'll always use this notation with respect to this initial metric D0. And when I've got a little tilde there, then I mean it's the ball in the image space D0 tilde Z tilde R. Okay, so this is the situation we're considering. Okay, so now we have an idea what this regular region is, but if you try and work with an F0 of this type in the proofs that we did later, it's tough. You need to choose a different F0. Well, you don't need to, but it's very helpful to do it. So what you do is, since G0 tilde is smooth, you just introduce distance coordinates on this little ball. So introduce distance coordinates, so you choose appropriately A1 tilde up to AN tilde in this image ball here. And then distance coordinates are always of this form here. So this is very successful, by the way, in the theory of Alexandrov spaces. They turned out to be very useful. And also in the theory of Chigo, Colding, and everyone else who got involved. Initially, Colding introduced distance coordinates and then modified them to get his regularity theorem. So there's, they just seem to be very, very useful for a lot of geometric problems for various reasons. Okay, anyway, we can introduce them because G tilde is smooth. That means if I go down to a really small R tilde, then I can be sure that these things are really close to being an isometry, right? So I get a 1 plus epsilon by Lipschitz map. That just means that if I take the difference between F0 tilde X tilde and F0 tilde Y tilde, of course I'm taking, this is a norm in Rn, so all my mods mean norm in Rn. Then that is lies in this interval here. 1 minus epsilon d0 tilde x tilde y, 1 plus epsilon d0 tilde x tilde y. Okay, so you've got this, it's by Lipschitz, right? I mean, that just means, so I write it like this, but of course, you can write it like this if you like, that this thing is less than or equal to 1 plus epsilon or divide by d0. This is maybe the way most people are used to it. Here I've missed out a few tildes. And that's got to be bigger than or equal to 1 minus epsilon for all x tilde in the balls where they're not equal to one another. So that's the usual by Lipschitz condition, but I write it like this just for simplicity, right? It just means it's in that interval. Okay, so yeah, but once you've done that, then what you see is, well, the first map I had, this F0, which we're just assuming exists, is actually, per definition, it's an isometry, because I gave D0 tilde was given as the push forward of D0. So that means you can just compose the two maps and you still have distance coordinates, right? So here's what I just said. D0 tilde and D0 are per definition isometric to one another, because D0 tilde is just the push forward of D0. And that means that then if you take the composition of these two maps now, you get a 1 plus epsilon by Lipschitz map. And they're also distance coordinates. You just pull back the A1 tilde up to AN tilde with F0 now. Per definition, the first map was an isometry. And then you've got distance coordinates, which are 1 plus epsilon by Lipschitz. So let's just put all that together now on one page and see what we've got. So here's this composed map is now their distance coordinates, and they're 1 plus epsilon by Lipschitz. Okay, so let's just put all of this together. One more thing we need before we put all this, so we see what information we have. Using this by Lipschitz map and Perelman's pseudolocality theorem, you actually see that your curvature's less than or equal to epsilon t for t in 0, 1. Okay, because your region is almost Euclidean, depending on how small your initial epsilon was, due to this by Lipschitz property we had. And that means you can use Perelman's pseudolocality and you get this here. So you notice I said we're using the by Lipschitz property and so on. There's a little bit to be done here because you're not starting at a smooth space. You can only work away from time 0, right? So you have to work a little bit to get this done. But what you do is you start at a time really close to 0 and you use this by Lipschitz property, and you can show, in fact, that this is the case. So there's a little bit of work to be done, but this is essentially just Perelman's pseudo-locality theorem combined with this by Lipschitz fact. Okay, there's a little bit to be done though. Okay, so once you've done that, and once we're interested, remember, I could just make this r tilde smaller and get my epsilon smaller. So without loss of generality, you just assume you have the same epsilon after reducing r tilde again. So, okay, a little bit technical, but let's get to the setup. So now I'm going to write down the setup. So putting all this together, after scaling once, you just scale the initial thing once, and you're in then. So if you you accept all of this stuff before, let's get down to the new setup. Okay, and this is what it is. You've got Ricci bigger than or equal to minus epsilon 0 squared. Curvature is less than or equal to epsilon 0 squared t. Just by reducing this r tilde again, I can get epsilon squared, epsilon 0 squared. My time interval is without loss of generality 0 to 1 because I just scale once, right? And then I've got a bigger time than I started off with. What else have we got? So this distance condition, I'm just going to write slightly differently. Well, the exponential function here, I can surely estimate from above by something like this. From below, sorry, so you get this, this new sort of distance estimates. Why do I write it like this? Well, it's just useful because it's very scale invariant for Ricci flow. So I prefer to use the fact that these estimates above imply these estimates here. And we've got this initial map, which I call F0, and they're 1 plus epsilon by Lipschitz on B10. Okay, so that's our setup. We've sort of...
Sorry, Miles.
Yes.
There's one question in the chat. Yes. Are there any conditions on M? So like compactness?
At the moment, no. Well, okay. So I'm assuming for the moment, just for the simplicity of the whole presentation, that M is actually, the solutions are smooth and complete. So let's just write that down here. So at any time, yeah, I didn't make this completely clear. So the solution smooth I wrote down, but I'll just assume that each time this is complete for all time in 0, 1. So it could be non-compact, right? Because we're in a region now. In fact, this is not necessary. You can really weaken this condition to just having that your ball is compactly contained in the initial M for the times you're interested in. But for the sakeness of presentation, let's just assume for the moment that MGT is complete for all t in 0, 1. Other than that, we don't need any conditions. Yeah, I should have mentioned this. Sorry about that. Yeah.
Thanks.
No problem. Okay, any other questions? Because now we've got the setup. I've got to... No, okay. Yeah. Okay, and the other condition is we're assuming that this D0 is smooth in the following sense. If I push forward the metric, then I get something which is given by the distance generated by a G0 tilde, where G0 tilde is a smooth metric, and without loss of generality, you can say it's close to the Euclidean metric, okay, because it's on some ball in Rn, so you can, without loss of generality, assume this is the case. Okay, so that's our setup, and now we can start to work with this setup and see what happens. Okay, what we're trying to do is show that G of t goes down to G0 smoothly for some smooth G0 on B sigma x0 as time goes to 0. So in this setup, we don't know anything about time 0 now. All I know is all of this, and we want to show that, similar to PDE type regularity results, then in fact, we're going to see that G of t goes down to G0, and G0 is some smooth space as time goes down to 0. G0 is a smooth Riemannian metric, sorry. Okay, so how are we going to do that? Well, there's essentially 4 steps to showing this, and the steps to explain them is not too difficult. So let's go through it. Oh, I said it's not too difficult, we'll see. First of all, you solve the following Dirichlet problem. You want to solve it. You solve the harmonic map heat flow with the evolving Riemannian metric. S is, of course, not time 0. You have to stay away from 0. Somehow you want, well, sorry, you want on the boundary of your ball that you've got F0, and you want some sort of condition that tells you that the initial value of Z is F0. For example, maybe you want that it continuously goes down to F0 as S goes down to 0, right? That's what we'd like to solve. If you can do that, and if these things are diffeomorphisms, then what you do is you do the push forward with the help of these maps, ZS, of the initial Riemannian metric, and I call this thing G tilde S, and it's defined for S away from 0. And now the trick is Hamilton and noticed, and she worked on this also a lot, if you do this harmonic map heat flow and you do the push forward, then the thing you get solves a PDE. It's called the Ricci to Turk flow. Okay, so I actually forgot to mention to Turk. He also, of course, was the first person to really look at this. It solves a parabolic PDE. Okay, so then you're in the realm of parabolic equations. And maybe we can get some ideas about regularity there. So let's keep going now. That's step 2. Okay, step 3, show that G tilde, so using PDE theory, show that G tilde, when it goes back down to S, you can extend that locally smooth to S is equal to 0. At the moment, it's just defined for S bigger than 0. You really want to get it down, defined for S is equal to 0, and smoothly down to S is equal to 0, at least on some local region. Okay. And, right, that's what I've said there. I went a bit fast there. Right, step 4, I forgot to mention, is you want to show that this implies that now just pull it back, the G tilde S with your Z, and you want to show that that means that extends locally smoothly to S equal to 0. So here is the strategy. Actually, we came up with a strategy pretty early on, and we worked quite a while on this strategy. And if you look at it, you think, okay, yeah, a lot of them steps are going to be kind of difficult, but it's going to be an interesting thing. But you might think also that this step is going to be a bit of work to be done there. It turned out that step 4, once you think about it a bit, you realize, well, step 4, once you've got step 1 to 3 done, step 4 just follows almost immediately. So I'm going to explain how to do step 4, assuming you've done step 1 to step 3. Well, remember, we're assuming we already know that our G tilde now is smooth right down to time 0. That means that all derivatives of G tilde are bounded. This is what this D here means. It's a derivative in Euclidean space. And it's also without loss of generality close to the Euclidean metric, right? And what does that mean? That means that all curvatures are bounded with, you take the norm with respect to G tilde S at any time, and all gradients are bounded, right? And then once you notice that, you say, oh yeah, but our initial G of S is isometric to G tilde S using this ZS. So that means you get for free, because they're isometric to one another per definition, this must be the case. But then you're in business, because then you say, well, if that's the case for all S, by the way, in the whichever region you're looking in for some small t here, less than 1, then you just use the standard sort of Hamilton procedure to show that in fact G of S is smoothly converges down to some smooth Riemannian metric G of G0. Essentially, they're almost ODE techniques, right? Because remember, the Ricci flow equation was, right, here it is. The Ricci flow equation is given by that. So now you see that G of S is going to remain bounded above and below by delta. And in fact, you can show it's continuously going down to something. And you just use sort of ODE techniques to show essentially that G of S does go down to some smooth Riemannian metric G0. So the good news is that step 4, once you've got step 1 to step 3, it follows very quickly. Okay, so it's not where you have to work. What are the problems then? Well, the problem is that you're starting from some metric space, right? So you've got to do an evolution of harmonic map heat flow starting from some metric space, right? It's not a smooth Riemannian metric or something. So, and it's only by Lipschitz. We don't have any differentiability or anything at time 0. And so the first question is, because of that, is there even a smooth solution to this Dirichlet problem? And secondly, you said, I remember I said, if they're diffeomorphisms, we do the push forward. Well, how do we know these things are going to be diffeomorphisms for s bigger than 0? This needs to be true if we want to define this push forward. So we have to have some way of showing that z at later times is a diffeomorphism. And here's our solution to this problem, is that you don't start with f0, you start a little bit later. So I see I'm running out of time. Instead of f0, you start at ft. What is ft? You just take the distance coordinates you get. It's just a map now, it's not necessarily a homeomorphism. And distance with respect to time t, but using the same a1 up to an you had before. Now, if you use the distance estimates we had before, you'll see that this means you're almost by Lipschitz, right? You see there's this little error, but this little error is not bad. It's a sort of scaled error. It's got to be taken care of, but it's scaling in the right way for Ricci flow. Okay, so that's the good news. So you start with these things. They're also not smooth, but they're close to being smooth. You can mollify them so that they're smooth and that this condition remains true. So that's not an issue. That's the good news. And then you solve. So here's the key idea, is that you start now at some small time t bigger than 0. And that's why I've got this little t here, because your initial time now is this little t, and you solve the same problem you did before, but with ft on the boundary, and the initial time is given by ft. So you shift everything to this time t, and you see that, in fact, this has a solution. So that's what you do instead of starting with f0. And yeah, well, you've got to show it's got a solution, then it has nice properties. And that's what we did. So what we did was we showed, in fact, that if you start at time t, for any t small enough, and your epsilon is small enough in this initial setting, which you can always reach, and ft is one of these initial values which we just I just described. Now you don't even need that ft are distance coordinates. It just needs to satisfy this almost by Lipschitz condition. Then you find a solution for a well-defined time interval. And here's the nice thing. If you flow long enough, so you just need to flow to 2t now. So for a short time t you flow, then all of a sudden your maps are now by Lipschitz. Of course, the by Lipschitzness here, this alpha is maybe not as good as epsilon, but it's certainly less than 1. And it's going to 0 when epsilon goes to 0. So you get the by Lipschitz property for later times. You have to flow for a short time before you can get it. Remember, we started time t. If you flow to time 2t, then you get, all of a sudden, you're in the by Lipschitz region. Okay, so that's the main thing we needed. And now you can imagine what maybe the solution, or how you go on now with the solution. Once you've got these things, to get your solution to the initial Dirichlet problem, you let t go down to 0 and take a limit of these maps, which I call zt, and that will give you your solution to the Dirichlet problem. Okay, the proof idea I'm not going to go into now because time's running out. I'm not going to go into details, right? The idea is this sort of scaling argument with quite a few. I mean, it's the main tool of the paper. There's a scaling argument and then various estimates. And the idea is that if you imagine, yeah, like a lot of things, right? The idea is that if you scaled everything, so you scale your solution, you scale to Ricci flow, you scale your maps, and you scale them appropriately. So you scale them in the right way so that the new things are still solutions in the same way they were solutions before. Then because the Riemannian curvature was like epsilon 0 on t or epsilon 0 on s, it's becoming very close to 0 once you scale to time 1. And the by Lipschitz condition guarantees, in fact, that you're very close everywhere to Rn delta, at least more and more you scale. And that tells you then also, this ft is close to an isometry, it must be close to an element in On. Yeah, this epsilon 0 by Lipschitz, you make epsilon 0 really small, and that means you're close to an isometry, which means you're close to an element in On. And then just imagine doing heat flow of this thing. It's a linear map, so it's not going to change much. And that's in fact what happens. It just smooths out, and you maybe lose a little bit, you move a little bit away, but it becomes smooth, and that gives you this nice, I'll go back to this slide here. This gives you this by Lipschitz condition then for later times. So that's the rough idea. Of course, I'm missing out technical details, but there's a lot to say about this idea. I mean, the idea is presented there. You then have to make sure that you get for all really later times that this works. So there's a bit more to do, but that's essentially the idea, one of the main ideas behind it, or the idea behind it. Okay, so let's just move on. Right, and now I said let t go down to 0, and you get this limiting map, right, said S, and that's then going to be the solution to finding that this thing's a diffeomorphism for later times, because it's now 1 plus alpha by Lipschitz. It's smooth, and now you can do step 2, and you can do the push forward. So you do the push forward, and you've got this well-defined smooth family of metrics, and now the rest of it's just essentially PDE. So the first thing is if you just reapply this theorem, which I just mentioned before, you see you do it for smaller and smaller epsilons by taking smaller and smaller regions. Then you see, in fact, that in the C0 sense that you are going back down, G tilde is going back down to this initial metric G tilde 0. So you get that just by reapplying this previous theorem for smaller and smaller epsilon. And as I said, Hamilton and Xi and de Turk, I think actually Hamilton noticed this connection between the harmonic map heat flow, though maybe de Turk also. I should be a bit careful here. At least he was involved in this whole Ricci de Turk flow here. It was his idea to look at this evolution equation. Now you see that G tilde solves the Ricci de Turk flow. So Ricci de Turk flow is a PDE. So you can start to do PDE type results now. So now you've got a chance to really, and we know already that it goes down to the C0 sense. So now you've got a chance really to show it goes down smoothly, because G0 tilde itself is smooth per definition. Okay, so what you do is, well, okay, so what we did, there are various ways, I'm sure, of proving now that G tilde is smooth right up to t is equal to 0. The way we did it is that we constructed a sort of competitor solution, which I just call L, which it's just constructed using standard parabolic techniques, has these initial values, and is equal to G tilde on some Euclidean, on the boundary of some Euclidean ball. Now you know this L is going to be smooth by construction. The standard parabolic techniques will guarantee that this thing's smooth. So we're nearly finished now with the whole idea. Okay, so that's smooth right up to time 0. And now the way we showed, in fact, that they are that G tilde is smooth was the following: up to t is equal to 0. We showed, in fact, that G tilde is equal to L, and the way we did that was we proved a new sort of theorem, which we call our L2 theorem, and that says that if you take two solutions to the Ricci de Turk flow, and they're defined on, and they're smooth on this ball here. Notice I haven't got down to time 0, I'm keeping away from 0, and continuous on the full space, and L is equal to G tilde on the boundary, not at time 0 necessarily, and you assume they're both close enough to the standard metric, then you get this L2 estimate here. Okay, you get that the later times, but here I've forgotten to write for t in 0t, you can bound your the distance in the L2 sense between G tilde and L by the initial G tilde and L2 distance up to some constant depending on n. And here, I haven't said what epsilon n here is. It needs to be small enough. Okay, there's some constant depending on n, that if it's small enough, then this here works. Okay. And that's essentially the way you do that. So once we've got that, we know that G tilde is equal to L, and we know then that means that G tilde is smooth down to time is equal to 0 because L is smooth down to time is equal to 0. And then we're in good shape because that tells us then that the whole problem is solved that way. And okay, so yeah, I guess, right. So one last point is how you might solve that, or how you're going to do this. What you do is you consider the following function. So this is the last thing. 1 plus, let's see if I can remember this, a big lambda times by, then I need here G tilde minus delta squared plus, that's at time t also, plus L of t minus delta squared. So if you look at this thing here, dt, just make sure I've got this right. Yeah, and you look at ddt of this lambda is some big constant depending on n, which is big. Remember I said that an epsilon n needs to be small enough so that these terms in here remain small, but they give you good terms when you look at the evolution equation. You'll find out that that thing is less than or equal to 0. So that's the help function that we constructed, which then shows you the L2 estimate and completes the proof. So I've gone a little bit over time. Sorry about that. Thanks for your attention.
Thank you very much. Are there questions, remarks, comments?